Hi, I'm Rahul, and today I will be talking about the paper called Understanding the Performance Implications of the Design Principles in Storage Disaggregated Databases. But first, an introduction. Storage compute disaggregation is widely adopted in the cloud as exemplified by the emergence of new databases. For example, Aurora DB, Alloy DB, Polar DB, Neon, etc. In this setup, storage and compute are connected via networking. This presents us with the following advantages: independent and elastic scaling of compute and storage, increased resource utilization, reduced cost, and fast crash recovery. According to the authors, storage disaggregate databases are based on the three principles. P1, here the compute and storage nodes are running different software stacks. For example, compute will be running the SQL layer, buffering, etc. And the storage will be running logging and storage. In P2, we only send the write-ahead logs to the storage on a transaction commit. Traditional databases had to write data pages back to the disk based on the buffer pool size pressure. However, the data pages are asynchronously materialized on the storage. And last but not the least is P3. As the data is shared between the compute nodes, we have eliminated the need to move data to the newly added compute nodes. The main idea of the paper is to study and investigate the effectiveness of all the principles that I just discussed via the following 6 questions. So they pose 6 research questions and want to tie back these questions to answer the principles. So the first question is how much performance overhead is introduced by storage disaggregation? This is relevant to P1. To what extent can buffering help in mitigating the performance degradation? This is again relevant to P1. And how significant is the performance improvement due to log as the database design? What is the performance impact caused by supporting multiple versions in the shared storage design, which is relevant to P3? How does multi-version storage affect checkpointing? And last, how effective are various log replay methods within multiple version storage? To mirror the approach followed by popular databases like Aurora DB and Alloy, they also investigate the design principles sequentially. By sequentially, they mean that the systems that we build are sequenced according to the principles. So for example, if we are investigating a system with P2 principle, we already assume that P1 has already been implemented and is integrated. Similarly, for P3, that means P2 has been implemented and integrated, and by P2 transitive, P1 is all. So this is like a layered approach which has been followed for the databases out there, and their system also, or their approach for experiments also follow the same approach. To answer the 6 questions, the team developed 6 architectures. The first one being the monolithic architecture. It's a traditional database with disk base running on a single node. We have log buffers and we have local buffers. Just to give a little bit more detail, so we have our PostgreSQL query engine, which accepts the SQL parsers, does all the magic. We create the wall logs, which we call the X log over here. We write them to log buffers. For a transaction to commit, we wait until all the log buffers corresponding to the transactions have been written back to the wall file. So log buffers is not a buffer pool, but you can imagine the wall logs are created as buffers pushed to log buffers. But for a transaction to commit, we have to make sure that log buffers or logs to a certain LSN have to be committed to the wall file. And local buffers are your traditional buffer pools, which contain the data pages of B trees or whatever database we have. So this is the first architecture. The second architecture we have is the remote disk one. Here we disaggregate the storage and the compute and run them on different machines. Here we can see that all the calls that we are making for storage are through RPC calls, right? For example, writing the wall log to the storage node, we need to make an RPC call to append the log. And to fetching the data files, we also need to use RPC call to connect to the second machine and fetch that data file page or whatnot. One way they did not mention, but one way to imagine this kind of setup we can accomplish very easily by having a file system, which is like an NFS, network-based file system. And then you can just make sure your wall log files and data page files are mounted to that file system. And then you can have the same system, nothing major code changes. And then you have the second setup. The third setup that we have is the log as the database. In this setup, the compute node is only sending the wall logs to the storage node. The actual data pages are actually generated by replaying the logs on the storage node asynchronously. So whenever the storage node receives a request for a page, the get page service checks if the page has been created, and if yes, returns it. Otherwise, it replays the log and returns the page. This is the fourth one, which is log as the database with multiple version storage. In this setup, we have multiple versions of the page. One thing to keep in mind is the primary compute node is responsible for all the writes. So here we can see that we have the primary compute node, which receives all the writes, and it sends for a transaction commit all the wall log records to the wall file. Wall logs are written in the wall file, and the log records are replayed using the replay process into some kind of a storage. Here they are using RocksDB. But one API change is present if you look carefully, which is whenever any compute node needs to get to a particular page, they make a request which is of type get page at a particular LSN. And it is the responsibility of the storage node to figure out if that LSN has been replayed or not. And if it has not been replayed, it will replay it till that point. Those pages will be written to RocksDB, and then it will return it back. So anytime another request comes with a lower LSN or whatnot, it will be returned immediately from the RocksDB. And the last one we have is the log as a database with multiple version storage and filtered replay. This is almost the same as the last one, but has a has a filtered replay technique to apply to the RocksDB. We can exemplify it using, we can show it by this example. So for example, imagine that you write to a wall log and the get page request comes for a particular LSN. We have to wait until all the logs from the replay starts to replay end have been applied, right? But in this case, the filtered replay is smart enough to say that only the first two log entries are corresponding to the page request. That means we don't have to apply all the logs till the end. We can only apply till to the first two and reply to the compute node immediately. But we have to apply all the logs to a particular position. So for example, if the log entry or the LSN was somewhere in the middle, we'll have to apply all the entries from the start to the middle and reply. But this helps in eliminating replaying a bunch of logs which are not relevant. And last is log as the database with multiple versions and smart replay. This is almost the same as the previous setup, but here our get page service is a little bit more smarter. One thing to think about is that when we send a wall log record, the wall log record contains the replay logs for a bunch of pages, right? So we can know by reading the wall log record, does this wall log need to be applied for this page or not? And in Smart Replay, what they do is that instead of replaying all the logs till a particular LSN number, they know the start LSN, they know the end LSN, and they can do a quick scan process to determine which log entries are pertaining to this page ID, and they will not replay those logs which are not relevant to this particular page to reply to the client, right? So for example, a request comes in and they determine out of 100 log entries, only the first and the fifth need to be replayed. So they will just play the first and the fifth and just reply back to the client. This helps in dramatically reducing the number of logs that needs to be executed during the critical path, which is to return back to the client. And in the background, they will continue asynchronously materializing these pages and putting in DB. The experimental setup they have for storage node, they're using 2.4 gigahertz systems, 188 gigabytes of RAM, 1.5 terabytes of NVMe SSD. For compute, they're using 2.3 gigahertz, 64 GB RAM, and 90 gigabytes of NVMe. Operating system is Ubuntu, and network is 10 gigabytes. So let's go over the results. The results are pretty interesting. The first comparison is between a monolithic architecture and remote disk architecture. In all the experiments, light workload means running a sysbench with a 30-second idle time between each runs. So they run a sysbench, wait for 30 seconds, run another iteration. In heavy workloads, there is no idle time. We'll get to know later why this idle time matters, because as we make more changes in disaggregation, the way your logs can be replayed, this idle time can have a significant impact on the read or the write performance. These graphs show running light workload for read and write with varying buffer sizes. So buffer size plays a role during read as pages can be cached. So increasing the buffer pool size, we don't have to read from the remote disk. So in the first graph, we can clearly see that as we increase the buffer pool size, both remote and monolithic architectures behave the same, because in this scenario, all the pages which are relevant for a sysbench or whatever our experiment is are already in the buffer pool, and we are not making any RPC calls, right? For the write workload, there's a huge discrepancy in monolithic and remote disk, and this is mainly because when we are writing to wall logs, the monolithic has to not make a network call. And for remote disk architecture, all wall logs and data files have to be going through the to the RPC calls, and that's why there's a big performance discrepancy. One thing to note, very interesting, is that the remote disk for 1 megabyte and 7 megabyte, there's a performance improvement. And the reason there's a performance improvement is because the bigger the buffer pool size, the longer your database can keep the dirty pages in memory, right? For light workloads, it does not matter in this example, because after say 700 megabytes, you can see the write performance did not improve. The reason being, after 700 megabytes, all the pages which were relevant to the workloads were already in the buffer pool. So increasing the buffer pool did not have any impact. We'll see the reverse when we have the heavy workloads. So for example, this is the one for heavy workloads. For heavy workloads, we can see reads has the same behavior, which is as the buffer pool size increases and matches, we never have to make a remote RPC calls, and we are fine. All right. That's why the performance is almost the same. For write workloads, if you see little bit more, I think it's not very clear to see, but for increasing the buffer pool sizes, the write throughput of the remote disk improves. And it improves because the larger the buffer pool you have, the more you can keep dirty pages, and you don't have to incur the cost of networking. And of course, monolithic wins here dramatically because you're not making any RPC calls. Next, we have the performance difference between remote disk and logDB. Read performance is mostly the same, as the cost is dominated by fetching pages from remote. And in both the cases, for remote disk and logDB, the most significant cost is querying the remote server for the page. And this is for read. For writes, it's also the same, because both the systems are just sending wall logs and not the actual pages. So we are fine in this case. For write workloads, for heavy workloads, the situation changes a little bit for write. So we can see in reads, it's still the same. We increase the buffer pool size. Remote disk and logDB are working mostly the same, because both have to make the remote call to fetch pages. And depending on the buffer pool size, both remote disk and logDB can contain this almost same number of pages in memory. For write workload, it changes dramatically. The reason being that it never has to flush dirty pages. Remember, as we talked previously, that pages are materialized asynchronously. Therefore, compute nodes have to never incur the cost of pushing the pages, right? So in logDB, we are only sending the vol logs to the storage node. There's an asynchronous process which keeps on materializing the pages and putting in some kind of a database or whatnot. But the good point being that logDB scenario, we never have to send back data pages back to the storage node. And that's why remote disk lags significantly as compared to logDB. The next experiment we have is logDB versus logDB multi-version. So reads is almost the same, same idea. We have enough size in the buffer pool, both make the same calls during read, and they have almost the same number of pages in the buffer pool. The main difference in the write throughput comes from the fact that we are incurring large overheads in maintaining bigger RocksDB instance. Because remember, in logDB, we are not having multiple versions of the same page. So we overwrite the page. But in logDB, multiple versions, whenever there's a log entry, we fetch the page, replay the log on the page. This creates a new version of the page, and then we append it in the RocksDB. So the number of pages present in RockDB are dramatically bigger. So we incur the cost of replaying, and we incur the cost of maintaining multiple versions in RocksDB. This is for the scenario where we disable ton pages. So let me go over what happens, what's the difference. So traditionally, all the databases, for example, InnoDB and Postgres, have to send a full page to the remote storage node to prevent ton pages. So what that means is, imagine you're trying to replace a data page in a B tree. If we overwrite at the same place, there can be a situation where you wrote half of it and you crashed. That means the previous page which was there is also corrupted. To avoid such scenarios, what InnoDB does is writes the full page somewhere else and then writes it again in the main page. So during in the recovery case, we are able to fetch the actual page and we won't have the corruption. Postgres follows a different approach, which is after checkpointing or some scenario, it actually sends the full page as a vol log entry. So that, for example, if you are trying to write to a data page and you crash, that means you have a half-written page which is corrupted, but you can recover that page from the vol log. But you can see in both the scenarios, we need to send the full data page back to the storage node, either through double write buffer or either through the vol log record and whatnot. So you have to incur the cost of it. In this scenario, they are showing, 1 second. Yes, in this scenario, they are showing that we don't have to, we are skipping the ton pages, because if we are maintaining multiple versions of the page, we don't need to send the full page image. So as you can see, for the write throughput, which is the write graph, the green bars are significantly larger than the logDB. The reason being that we have skipped the full page sending, and this is giving us the performance boost. And last but not the least is logDB versus logDB multi-version and logDB multi-version with smart read. As you can see, the read performance of these systems is almost same, because once this read workload, we don't do much. If the pages are in buffer pool, we are good and get the same performance. All of them have to contact the remote storage node, so they incur the cost of networking. The write performance is better for smart read because we have to apply less number of pages to reply back to the compute node, and this shows up as a performance improvement. Fast replay is the one where we said that if we have 100 log entries and we know that our log entries relevant to the page is still only 40th position. We don't have to play the rest of the 60. This is giving us the performance improvement for fast replay compared to the log DB MV. So the conclusion here, after doing all these experiments, we try to answer back the same 6 questions that we had in the beginning. How much performance overhead is introduced by storage disaggregation? So significant performance reduction for reads and significant performance reduction for writes. Accessing storage over network is slower. Second question, to what extent buffering helps in performance degradation? Buffer helps in the compute node for reads. Buffer does not help significantly improve your write performance, as the compute node always has to send logs. Third, how significant is the performance improvement due to the log as the database design? Not much performance improvement for light workloads. Under heavy workloads, the performance is significant. Again, remember, for log as the database, we don't have to send data pages, they are being materialized. Read after, the other thing that they mention is the read after write. So read after write is a situation where you write a certain, you commit a bunch of transactions and you try to read the data immediately. Remember, the pages are not materialized on the compute node. So you always have to go to the storage node and wait for the page to materialize. And this is where there can be a performance overhead compared to monolithic. What is the what is the performance impact caused by supporting multi-version pages? When we have multi-version pages, enabling torn page writes reduces write performance, right? Because you have to send the full pages. But when we disable it, multi-version definitely shows improvement. How does multi-version storage affect checkpointing? Checkpointing is essentially free when we have multi-version storage engine, because we can figure out the LSN number, and RocksDB is already maintaining multiple versions of the page, and we can checkpoint that one. And how effective are the various log replay methods within multiple? So different log replay methods significantly improve the write performance based on, as we saw during smart replay and filtered replay. Filtered replay, we reduce the number of logs that need to be replayed. Smart replay, we figure out the logs pertaining to the page entry. We only replay the particular logs. So all these methods reduce the amount of compute that you have to do. For example, playing the logs and inserting in the RocksDB, and this can show up in your improvement in the write performance. That's all. Thank you.